Hi everyone, thanks for joining me. Today I'm going to talk to you about Houdini and why I think it's very interesting for medical animation, and why hopefully if you're using a different package, by the end of the talk you'll consider switching over to Houdini. So I have to mention that I have only moved over to Houdini a couple of years ago. Before that I was always using Maya. That's kind of where my background is. It's back when you still had to learn things from textbooks. And all of the comparisons I'm making, just as a bit of a disclaimer, all of the comparisons I'm making compared to Maya, that's what my frame of reference is. I don't have production experience with something like Cinema 4D or Blender, so that's the context basically. But during all those years that I was using Maya, I always had a bit of a preconception about Houdini. And I think that's like the preconceptions I had about Houdini are probably quite common. And so I thought I'd share them with you here just so you see if that resonates with you, and to see how we can debug those. So I always thought that Houdini was really mainly something that people used for difficult particle effects. And so we're talking about basically whenever you needed to blow stuff up. Apart from blowing stuff up, I knew that Houdini was really good at doing things like smoke effects and fog and clouds and shattering things and water and ice and those sorts of effects. And so you do a couple of tutorials, have a look at what the software looks like, and then you're faced with something like this, where you've got a whole bunch of code on there, you've got these node networks that look confusing, and then you've got a whole table full of data that you don't even want to look at. And so I would just do a great big nope and run back to Maya, where everything was a bit more comfortable and a bit more familiar. It's not that scary. Really, it's not that scary. It's just another program, just like any other program. It's not inherently more difficult than learning how to use Maya. And the advantages of Houdini, I think, are significant. And particularly when you're doing medical animation like we are, Houdini has some features that are very relevant to us and that will help us make things look both more scientifically accurate and, I think, prettier. So before I go into a lot of detail with case studies and examples of things that you can do in Houdini, just a few quick words about us. So I'm with Phospho. We're a small London-based medical animation company. We tend to do a lot of work on the cellular and molecular side of things, a bit less so on the anatomical side of things. So we're doing lots of oncology projects, lots of immunology projects, things like that. We work with a series of amazing clients, both in academia and in industry. And here's our latest show reel to give you an idea of the sort of work that we do. Okay, so let's move into talking you through a bunch of features of Houdini. And I think when you move to Houdini, it's, like I mentioned, it's not necessarily a much more difficult bit of software than any of the other bits of software that you're used to using. But as with any type of software, it always really helps once you start to think about things in the way that the software likes you to think about things. And so when it comes to Houdini, it's all about data, and particularly about points. So if you have any type of geometry, let's say this cell that you just saw in the show reel, Houdini likes to think of this as a big collection of points that are connected. The real click is when you realize that all of those points you can manipulate with infinite granularity. So basically, you've got massive control over whatever it is that these points are doing on a per point basis. You can do things to the entire object for sure, but you can also manipulate each individual point in a way that's really, really difficult to do with something like Maya. So in the case of this cell, for instance, we did a bit of a simulation to help it crawl across the surface. But in particular, I'd like to point to the microtubules that you saw move and stay connected throughout. And so the way that this works is that we just scattered a bunch of points on the nucleus. We scattered a bunch of points on the membrane. We connected those points from the nucleus to the points from the membrane and just basically told it to stay connected no matter where the cell's going and how it's crawling. And then extruded those, and voila, you've got microtubules that are behaving according to the way that the simulation is running. So that sort of thing needs a particular level of detail and a particular level of control over what points are doing. That's really quite straightforward to do in Houdini, but it can become really quite difficult to do in something like Maya. So I think that's definitely a really big plus. The other thing that Houdini can do is, and this is kind of implied by the fact that people use it for such big particle simulations, is that Houdini is really quite good at dealing with large numbers of things. And so here you see an image of a tumor that we made that's being attacked by immune cells. And because we do so many oncology projects, we've built quite a few digital tumors during our time. And when you do it in Maya, roughly 50,000 cells seems to be where things start to slow down quite rapidly in Maya. So this tumor that you're looking at now that we made in Houdini has got nearly 1.5 million cells on there. And so that gives you a real sense of scale, and it makes an image much more impressive. And Houdini is just better able at handling those large numbers than Maya is. And I think that's for the type of work that we do, it's going to be really important. And because you're making these things essentially by algorithm in a procedural way, you're not hand placing all of these. You get a particular level of detail and intricacy that would be really difficult to do by hand. And so, for instance, this is a similar setup, but we tweaked some of the parameters slightly so that it starts to branch, and you can think of this as a tumor being mid-invasion and metastasis. And so that level of intricacy and randomness is really, really difficult to do yourself in Maya, but the kind of procedural setup that Houdini allows you to build makes that quite simple. So what you're looking at here is a still from a project that we've done for Oxford Nanopore with a nanopore embedded in a membrane and some DNA flying around. And I'd like to in particular talk about the membrane here. This level of intricacy and detail in the membrane, it makes it almost look like it's something out of a molecular dynamics simulation. All of this was done directly in Houdini. So what you're looking at here is essentially a thin box filled with points and a space-fill algorithm connecting those points in a way that naturally avoided intersection. And because it can avoid intersections, you get this really tangled, complex look that is especially suited to making in Houdini, and it's not necessarily something that would be straightforward to do in a different package. And these sorts of space-fill algorithms can be really, really useful because this is one application of it with loads of connections that are each of them really, really short. But another application could be something like packing the DNA inside of this virus, where we have this volume of a virus and a single spacefill algorithm is just connecting all of the dots. And so you find time and time again with Houdini that you build a particular type of setup, and then afterwards you find out that actually with some minor tweaks you can use the same type of setup in all kinds of different applications. It's really, really useful. So when we're using points to create these intricate bits of geometry, it's not just a matter of kind of spacefill algorithms and connecting the dots and that sort of thing. You can also think of organically growing things. And so in this case here, we've got another nanopore project with a particular well that's growing around a bunch of sequenced DNA. So if you're doing any kind of organic growth, then that's something that Houdini is really, really quite good at. So in this last example that I want to show you here, we used a bit of math and a bit of a tiny bit of coding to basically mimic what a soft body simulation would look like. And so the fact that none of these cells are intersecting, but they're looking like they're bunched up against one another, none of that was done with time time-intensive, expensive soft body simulations, all of that was done directly with like a tiny bit of math, a tiny bit of code, and it looks really quite similar to what a soft body simulation would give you, except that it's way, way faster. So because Houdini is so good at dealing with data, it kind of makes you wonder what other kinds of data you can get into Houdini and what sort of things you can make with them. And so the first example that I've got for you here is some proteomics data. And this is based on a project that we've done with Chris Tape at the UCL Cancer Institute. And they do a lot of really interesting proteomics research where they're looking at how signaling networks inside cells are connected to one another. And these enormous proteomics data sets, there's so much data in them that it can be really hard to visualize exactly how the connections between the different signaling hubs work. So what you're looking at here is a visualization of that data where all the spheres are signaling nodes that they measured. All the sizes of the spheres are relative to the abundance of the signaling of a particular node in their data set. And the connections between the spheres are connections between those signaling nodes from their data. In Houdini, you can make this dynamic. And what I mean by that is we can put a force on each of those connections, a bit like they were connected by a spring or an elastic band or something like that. And that force we can link to the original data. And so what that means is that if two signaling nodes are really strongly connected in the data, we can give the spring a really strong force and they're pulled together a little bit more. If some connections are a little bit weaker in the data, the strength of that spring is a little bit weaker and they're further apart. So you put all that data in there and then you basically let the simulation run and it organizes itself in the sort of optimal way through the dynamic simulations inside Houdini. And it gets really interesting that you can then visualize different conditions and see how the networks change when a cell undergoes division or something like that, where the entire signaling pattern just changes and it rearranges itself. All of that being driven by the original experimental data is really exciting. Another bit of data that we deal with on pretty much a daily basis is protein structure data. Protein structures, I don't know if you've ever opened up a PDB file in a text editor, but essentially it's just one big data table with atomic coordinates and some additional information about what the atoms are, what amino acid they're part of, what their number is, those sorts of things. But it's just data, and then you have amazing plugins like Molecular Maya by Clarify for Maya that allow you to import that and visualize it as an actual object with a ribbon structure or surface structure or something like that. Now, the great thing with Houdini is that it lets you natively import that sort of data as just atomic coordinates and points with attributes on it. It allows you a level of control that if you're working with an external plugin, you don't necessarily have that level of control. That's not to say that something like Molecular Maya isn't a fantastic plugin. It absolutely is. But sometimes it's nice to be able to get down to the original data and manipulate it yourself. And so Houdini allows you to do that. I'll show you a tiny bit about that a little bit later on. So when you're working with protein structure data, one thing that's always particularly difficult to do in a program like Maya is doing conformational changes. And so it's interpolating between one shape that a protein can have to a different shape that a protein can have. And the reason for that is for Maya to do a blend shape, what it needs is the two objects that you're interpolating between to have the exact same poly count, to have the exact same point count, to have everything laid out in the exact same way. And that's really difficult to do when you're importing stuff with a plugin. Basically, the geometry will never be quite exactly the same. And so it'll be difficult to do that. So the reason, what we used to do was to literally put a skeleton all the way along a protein and then manually mimic that conformational change. It would be really quite laborious to do, and because you're manually doing things, it would be going a little bit further away from the original data. Now, there's probably a better way of doing it, to be honest. But yeah, that's how we used to do it, and it wasn't the most accurate way. So when it comes to Houdini, because you've got all these coordinates and it's importing it as a point cloud, you can do all of that kind of interpolation before you've meshed anything. And it makes it really easy to do these sort of conformational changes. And so the video that you're looking at the moment, we did for the Leuven lab at the LMB in Cambridge. And the really interesting thing here was that they solved the structure of this DNA motor in all the different conformations. And it was for us literally just a case of importing them into Houdini and interpolating between them. And you then get this molecular machine directly from the data. And so that didn't require any hand animating, any matching of conformations by hand. It was all done directly from the data. And yeah, I think that's a really valuable approach. Okay, so that was protein data. Let's move on to DNA data now. So here you're looking at an image from that recent animation for Oxford Nanopore. They were kind enough to share with us an enormous amount of DNA sequencing data. And again, it was a massive data table that we were able to get into Houdini and to have this sequence of a single strand of DNA. After the helix has been unwound, you see the single strand of DNA with different colors depending on which base it is, and highlights. So in this case, the gold highlight is representing a methylation site. Now, all of this, we didn't randomly assign these methylation sites or these base calling IDs. All of that was based directly on the data, to such an extent that we could have this entire data set with nearly 190,000 bases sequenced. We could all visualize that in one great big sphere. And as you can imagine, that was also done with a space-fill algorithm, like I was mentioning before. And so doing this kind of data visualization, at this kind of scale is really quite interesting. And it's not something that I'd even remotely know how you would tackle it in Maya. But Houdini makes that sort of integration possible. And if you then move up to a higher level in terms of anatomy, there are ways in which you can get MRI slices imported into Houdini as well. And like always, you've got lots of freedom there then to go and manipulate them in interesting ways. Right, so that's data visualization for data that you can have from inside your body with protein stuff, with DNA sequencing, with medical imaging. And you can even go one step further and have a look at some data visualization of population statistics and those sorts of things. So here is a visualization that we're working on at the moment to do some coronavirus case tracking in London. So what you're looking at here is a map of London where we took some GIS data of the boundaries of all the boroughs in London. On top of that, we used some OpenStreetMap data to put some roads in there and to put the location of parks and waterways and basins and that sort of thing in there. And then on top of that, we could add data of how within each borough over time the coronavirus cases have expanded. And so it's particularly interesting here that you can see that during the summer everything was quieting down, and then autumn comes and we're in that second spike. So let's briefly talk about node networks, because you may not have used them very much, and Houdini, everything that you do in Houdini is based off of node networks. And the way to think about it is that basically every node that you put down is an operation. So instead of you going to a particular menu in Maya and doing a particular thing inside that menu, you drop down a node and everything that you would have done from your menu in Maya is inside that node. You build a network, and that network is really nice and clear, and you can trace back all of your steps, and it's a lot less hidden than your history in Maya is, for instance. So the history in Maya, that information is there, but it's not laid out in such a clear way as node networks can be. And so the nice thing about those node networks is that they help you become really efficient at particular kind of repetitive tasks. So let's head over into Houdini and let's have a quick look at an example. Okay, so here we are inside of Houdini. I just wanted to show you a quick example of how that efficiency with node networks works. So what you're looking at here is your typical Houdini scene. On the left, you've got your viewport. On the bottom right, you've got your node network. On the top right, you've got the settings and attributes and things for the node that you've got selected at that moment in time. Now, I'd like to show you some protein structure tricks. We've got a longer tutorial out there. I'll mention a little bit later on. So for now, here I've imported 3 structures off of the PDB, and these are coronavirus proteases. three structures, different structures bound to different drugs, and they're all slightly different from one another. So I've selected one here, and immediately you can see that it's imported it as a point cloud of atomic coordinates. And if we go and have a look at our spreadsheet, then you can see that you've got your coordinates for all of these points, and then you've got all that other PDB data in there as well. So you've got your chain, you've got the element, you've got which amino acid they're part of, so you've got your serines and your glycines and your phenylalanines, etc., etc. So let's use that to manipulate things a little bit and build our own ribbon viewer. So we're going to go straight in and code a little bit, and don't worry, it's just a single line of code, by putting down a wrangle. And what we want to do is we want to focus on these CAs. So these are the alpha carbons, and if you do a ribbon representation, you want to connect those backbone alpha carbons. So in order to connect those, we need to first group them. So you group something with coding in Houdini by just going @group backbone, and we then want to select in the attribute called name. It's a string attribute, so we do string @name equals CA. Oh. Great. So now, if you hit the I, you can see here that we've got 307 points selected, and those are in our backbone. Fantastic. We then want to hit blast, connect it up, and then we want to blast away everything that's not selected in our backbone group. If we have a look now, we've got significantly fewer points left. So this was before, and this was after. So these are all the backbone points. We then put down an add node to connect them together, link it up, and there we go. I mean, we've got our backbone here now, but it's a little bit jagged, and so we want to just smooth that out a little bit. Just put down a subdivide, have a look, maybe give it 2 subdivisions, nice and smooth. And now it's still just a string, so let's give it a little bit of thickness with a polywire. Hook that up. It's a bit too thin for me. Let's make it a bit thicker, give it maybe 12 divisions, something like that. There you go. It was that quick to make your own ribbon view. And of course, you can play around with that scale of that radius of the ribbon. But one of the really neat and efficient things that you can do, let's say you don't want to have a look at this structure. Instead, you want to have a look at this one. You don't have to do all of that again. You can either just connect your new structure that you want to look at into the first node, and there you go. That's all it is. Or what you can do is just copy these across. Just copy these across, wire them up, and before your polywire, put down a sequence blend. Connect everything into your sequence blend, put your sequence blend into the polywire. And so what the sequence blend is doing is that it allows you to interpolate between those 3 different conformations for the 3 different drugs that are bound. And so here in our sequence blend, if we go from 0 to our 0 input, our 1 input, and our 2 input, if we go between 0 and 2, you see that we can go between these different conformations. And if we put that same polywire in, it does the same conformational changes without any kind of error. And so this is something, like I mentioned, that is really quite tricky to do in Maya when you're importing all of these structures separately. But here, because you can still manipulate things on a point level before you put your polywire, your mesh on top of it, you have all that control to do these things. And if you want to get really fancy, you can put some kind of a sinusoidal expression in your input blend, so it kind of, in a sinus wave, goes from 0 to 2 and selects these different inputs one by one. So let's import that bit of expression, and if you play it now, you see you've got that wiggle, so it's going back and forth between these 3 conformations. And if you've got a few more of these types of conformational changes, you can simulate some sort of Brownian motion in that kind of way. And it was really that easy. Like the efficiency in Houdini is fantastic. Okay, back to the slides. And that same sort of efficiency you get across the board. And so before I was showing you it with protein structures, but with something like map data, you've got the exact same thing. And so here is that map of London with all the different boroughs with their domain boundaries. And we did that coronavirus, the visualization where you extrude everything based on the number of cases that particular borough has had over time. But let's say you want to look at, instead of coronavirus cases, you want to look at some population data, see how many people live in each borough, because that obviously has a big impact on the number of cases. Instead of having to completely redo that same visualization, all that we had to do basically is to pipe in a different Excel table at the start of it and tell Houdini not to look at the column called cases, but look at the column called population count. And then all of a sudden you've got your population count. And so going from one visualization to the next, in this case, it took 5 minutes and that was it. And so it's really, really efficient. And the great thing is that efficiency means that you have to do less of the kind of boring, repetitive tasks, and you can spend more time actually getting to the nitty-gritty of creating these interesting things. So I've shown you some things that you can do in Houdini that are quite difficult to do in other types of software. I've shown you what kinds of data you can get into Houdini. I've shown you that for a lot of things, Houdini is way more efficient than other types of software. And there's another really important thing that I think I should highlight, and that's cost. And so, when we're making animations, we're using all these different types of software, and none of them are really that cheap. And when you've got your animation package, you've got your renderer, you've got your Adobe suite because you need to edit stuff together, you've got maybe some sort of compositing software. All of these software packages, the pricing for them, it just adds up and it adds up and it adds up, and none of them are perpetual anymore. You have to go for these annual licenses, and it can be quite a big burden, particularly when you're just starting out. So this is what Maya is charging you these days, and this is what we were paying for Maya annually, $1,600 for 1 year for a single license, and it's quite expensive. And so what Side Effects have done is that for Houdini, they've split up different tiers. So the top tier for big studios is quite expensive. But then they've got this indie tier, Houdini Indie. It's for small studios and it's for independents. And if you get Houdini Indie, a license will cost you $269 a year. So you pay for Houdini Indie annually a little over what you would pay for Maya for a single month. And I think that's absolutely fantastic. And it really makes a difference. The other thing is that Houdini has these educational licenses, so it's even cheaper if you're an educational institute. And on top of that, if you don't mind having a watermark on your renders, then you've got Houdini Apprentice, and that's completely free. So it's not a 30-day free trial. No, it's just completely free. So let's say you've been watching me praise the virtues of Houdini, and you want to give it a try, but you don't exactly know where to start. I think it's probably useful if I show you a few places that you can go to for some great tutorials. Now, the first one I have to mention, of course, is Antagma. So Antagma, they've got a massive tutorial channel. They've got loads of free tutorials. They've got even more in-depth courses over on their Patreon, which I can really recommend. Loads of tutorials about particular things that are really, really useful for making really intricate, beautiful effects, like space-fill effects or creating intricate geometry, those sorts of things. When it comes to Antagma, I'm not particularly objective because I've worked with them in the past to make a tutorial about how to use Houdini to show protein structures. And definitely, if you're interested in this sort of thing, go and have a look at it. The other thing that Antagma have done is they've got a really great 5-minute Houdini tutorial series where if you're a complete beginner, that's a really, really good place to start. Another tutorial channel that I can really recommend is 9between. They're over on YouTube. They've got the series Houdini Isn't Scary, Vex Isn't Scary. Vex is the coding language of Houdini, and that's a great tutorial channel as well. And then lastly, I wanted to mention CG Wiki. They're not video tutorials, but Matt Estella from CG Wiki has made this enormous database of how to do all kinds of different things. And he's been very generous in sharing all of the project files as well, so you can download them and go and have a look at things yourself. The elephant in the room when it comes to Houdini is obviously the coding part of it. And I just wanted to mention that apart from the fact that all of these tutorial channels do a great job explaining how the coding works, I'd never coded a single line in my life before I started using Houdini. And all of these channels did so much in explaining how the syntax works, how that way of thinking works. And I mean, still, in most projects, I'd probably just use 1 or 2 or 3 lines of code and that's it. But sometimes you want to do something a little bit bigger, and these resources will really help you kind of get to grips with that. So I wouldn't worry too much about the coding. And on top of that, in the past few releases of Houdini, they've really tried to make it more user-friendly in giving you all kinds of nodes that can do some very common things that you might do with a bit of code, but then now there's just a node for that. Right, so that's it for me. Thank you so much for listening to me. Before I go, I just wanted to quickly mention that if I managed to intrigue you about Houdini and you'd be interested in learning more and working with us on some projects for amazing clients, both in academia and in industry, we're hoping to recruit for a junior Houdini artist really quite soon. Great, thanks. Now let's move over to a live version and do a bit of a Q&A. Thanks.
Wow, great. Thank you so much. That was a very interesting talk, especially as someone who currently works in Maya and has sort of dabbled in Houdini a little bit. Very fascinating to see. Definitely encouraged me to take a look at Houdini again this weekend. It was easy to get overwhelmed, like when I first started, just it being such a different way of thinking from working in Maya. So yeah, it's
think
interesting.
Back to the first time you opened Maya.
That's true. Yeah.
if you come from, let's say, if you come from Photoshop and the first time you open Maya and you see all the different menu sets, and it you know that is overwhelming as well. But it's something that you just have to plug away at for a little bit. But luckily there's so many tutorials and there's so many
resources. Yeah,
and it
And it's always so encouraging to see the kind of results you can get from Houdini that, otherwise I'm thinking about how I would do that in Maya and it's like, oh God, my computer. Yeah, effectively.
Exactly. Yeah.
All right. So let's move on to the Q&A. We have a couple questions in the queue. The first one is from Alex Young. He asks, he says, thank you so much for the presentation. I haven't had a lot of exposure to Houdini and like you, really figured it was for complex simulations rather than for general tasks. I can definitely see how it's a powerful tool for molecular renders and for when you have data sets. But how have you found it for general modeling, let's say on a macro scale, or for more editorial content?
Yeah, that's a good point. I think it's so for like at the end of the day, apart from all the sort of generative procedural stuff, like it's still just a core animation package. And over the last few releases, Houdini have done more and more to kind of make the sort of standard stuff that you would do in other types of software much easier to do. And so, for instance, in the latest version that they came out with about a month ago, they put loads more rigging stuff in there, so it becomes quite a bit easier to rig stuff up than it was before. Now, I have to admit, though, like this is maybe sort of my dirty little secret. I cannot draw and I cannot sculpt. Like those are the two things I can't do. So if you give me a bit of software that is able to do all that sort of thing by algorithm, fantastic. Because if you put me behind ZBrush, I'll be there for a year and it'll still look hideous. So for me, in that sense, like having something that's procedural really works. But if you do use ZBrush quite a lot, then like with if you were using Maya or Blender or whatever, you can, of course, just export it out of ZBrush and get it into Houdini and then play around with there. Yeah, and then when it comes to editorial content, I think like that's exactly where Houdini would shine, I think, because like if you see editorial content as stuff like journal covers or those sorts of advertising type images, getting all that intricate detail in there it's gonna, like, that's exactly the type of use that you'd want that for. That big 1.5 million cell tumor that we're showing you in the talk, like that was a journal cover because, yeah, I mean, out of all the submissions we did, they picked the one that looked the most complicated. So, yeah.
Okay, so as a continuation to that question, how far do you feel like you can use Houdini as a full-on complete replacement for Maya in terms of like things like rigging or just other aspects of animation?
So I mean, I only use Houdini these days. I like no Maya whatsoever anymore.
Gotcha. I see.
And it's there's been that kind of a period where I was switching in between them, and you kind of go back and forth, and before you know it, you get really annoyed with Maya because you just want to manipulate a single point and group it and do all these things with it, and you can't. It really sucks.
Right.
Yeah.
So you're not using Maya at all, and I guess if you were to give any advice, do you feel like there's any other kind of benefit or advantage of Maya over Houdini?
So I think it's definitely, like I sort of briefly mentioned the rigging part, where those sort of classical character animation type things are probably still better in Maya. Yeah, but that's not, like I said, in the type of projects that we do, that's not really something that
Right.
I'd miss.
Yeah, no, I understand. Especially, I think in our field, the character animation isn't quite as prominent, or there's not much use for it. So yeah, I understand that. Great. So we have another question from Annie Campbell. She says, "Hi, Jeroen. Could you talk about the actual process of switching? So issues about running software in parallel, alembic transfers, etc., versus just making the jump and porting everything across?"
Yeah. That's a good question. So if you want to switch, then your natural inclination would kind of be to, well, at least it was for me, to kind of dip your toe in a little bit, and then for a while use Houdini as you would use ZBrush, where you're generating assets, and then afterwards you're putting them across into Maya. There's a syncing plugin for Maya that helps you sync stuff if you want to. But yeah, so I was using Alembic transfers for a long time, and the thing to keep in mind there is that you've got instead of just exporting a bit of geometry like you would from ZBrush, you're exporting large high poly count simulations, and so before you knew it, like a single project would have like 200 gigabytes worth of Alembic files associated with it, and then if you do cloud rendering, then you have to upload all that stuff to the cloud. If you see it and you go, I should have changed this little setting, you have to go and do that export again. And so I just got annoyed by waiting for this bloody Alembic transfer exports to finish, and I thought, well, how hard can it be to actually just render the damn thing in Houdini? Turns out really easy. So I'd definitely, like, for a time, I can imagine why people would want to do them in parallel, but then just make the jump, and do it on a when you're just starting out with a new project and got it, actually, I'm make that decision to, as a trial run, do an entire project in Houdini. It's not scary. It's gonna be fine.
We have another question from Avesta. She's curious about what render engine you use, and if you still use, I guess you kind of answered this, but if you still use any other, aside from Maya, 3D modeling software in conjunction.
Oh, rendering. So when I just started out in 2014, I was using RenderMan because I'm a Pixar fanboy at heart. So that was the go-to for a very long time. RenderMan is fantastic, but it's CPU based and it's slow. It's slow, and we were too slow to render entire projects in-house, and so we were using these cloud rendering services, like Zinc, the Google Cloud one, which sadly is shutting down a year from now, which really, really sucks. But we were spending so much money on cloud rendering, like it just thousands and thousands and thousands of pounds a year. And I realized that actually GPU rendering is pretty good these days. And in fact, it's like I can't really tell the difference anymore. So earlier this year, when we kind of made the full-time switch from only using, or like from using Houdini next to Maya to only using Houdini, I thought that was a good time to learn a new rendering package as well. And so we've been using Redshift, and yeah, especially with the new GPUs coming out when they're available again, like it's so quick. As in, we're talking 1080p final quality renders in 2 minutes rather than 45 minutes. So it makes a difference.
Amazing.
Yeah.
A question from Paul Kelly. Similar question, but beyond the 3D portion of the pipeline. At one point, you mentioned the costs of the Adobe suite as well. Was that to imply Houdini also has image video editing or compositing capabilities? And if so, is it possible to do an entire animation project all within Houdini and export a final compressed movie file for delivery?
That's a very interesting question. So there is a... Houdini is such a big program that there are these sort of weird corners of Houdini that people don't necessarily talk about, and the sort of wizardry of the people that know how to use it. And there is the possibility to do compositing with Houdini, but I think it's not kind of production ready, and it's not something that I'd recommend using. But the thing that I was more implying there is that we've at some point switched from using Adobe software to using DaVinci Resolve, so that you've got your editing software and your color grading and Fusion, your node-based compositing, and Fairlight, your audio mixing, all in the same software package. And there's a free version that does everything up to 1080p, and there's the paid version that does everything above it, which is, I think it's a perpetual license for $250 or something like that. It's ridiculous. So like we're in the process of switching things across to DaVinci Resolve at the moment. So that was probably on my mind when I was referring to how expensive Adobe software is. But yeah.
Comment from Stuart Jansen, +1 for Fusion, Redshift, and DaVinci Resolve.
Good.
Another question from an anonymous attendee. I'm wondering what your thoughts are on the new Bifrost node-based visual programming system in Maya, I guess, for simulations. I don't know if you've tried it or if they're even comparable.
So I have to admit that I haven't used Maya in quite a while, so I don't know about the latest versions. I know when Bifrost came out, it was very much like a fluid sim thing, and they had these amazing tutorials about like making oceans and things with Bifrost. It's just something that I never really had to use because it's so rare for us to do any kind of fluid sim, like things like fluid and smoke and explosions. Like how often do you get to do those things on a medical animation? I think I've made some like splashes of a drop of blood or something with Bifrost, and that it worked, but it's not something that I've used often enough to be, and I'm not familiar with the new versions of it, so I'm afraid I can't quite give you a satisfying answer to that. Sorry.
Yeah, no, that's totally fair. And I think we have time for maybe one more question from Jenny. You mentioned that you use a cloud renderer. Now that Zinc is shutting down, which alternative cloud renderers are you guys considering?
So, yeah, it's such a shame that Zinc is shutting down. It's just, I'd recommend switching to GPU rendering. You know, that's really it, to the point where on each project we were spending enough on cloud rendering that you could buy a GPU per project. And so, you know, yesterday unpacked my shiny new 3090 that we can run things now because we're saving all that money.
Ooh.
And so literally it's that's what I do. There are cloud rendering services for GPU rendering, but Grid Markets is one that I've dabbled in, but to be honest, it's so quick that
Yeah.
I've rendered an entire project over a weekend. It's super fast.
Wow, that's quite amazing. So do you guys use a render farm, or are you relying on just a few computers to locally
So
to?
what we don't use render farm. We've got a few computers that each of them we're trying and shoehorn in as many GPUs as we can, and then we've got a little local network, and we're using Deadline, the render manager client,
Mhm.
and I've got it all set up so that basically if I can hijack other computers for rendering, and it works really well, and it's super efficient.
Wow, that sounds very efficient. That sounds good. Yeah. Yeah. All right. Well, I believe that was our last question. So to all the attendees, if you have any burning last minute questions, speak now.
Or just drop me a line at my email address is jeroen@phospho.co.uk. So as soon as you figure out how to spell my name, then that's where to find me. And if you've got any other questions after the talk, then just drop me an email.
Great. Thank you so much
Great, thank
for
you.
coming to UnCon and giving this fantastic talk. Yes, thank you so much.
Great, thanks.
Great. Thank you.